Good morning, I'm Joe Goodman. I was department chair from '88 to '96, and I think I'm the one responsible for missing the 100th anniversary. I've been asked to give a very short introduction, but I find it quite difficult to do for our next speaker, Kristina Johnson. She is Stanford to the core. She received her BS, MS, and PhD degrees from Stanford in electrical engineering. And after a postdoc, she went to the University of Colorado, where she eventually became director of an NSF Center on optoelectronic computing. She also, while she was there, founded a company by the name ColorLink, which made optical devices that found widespread application in 3D TV and related technologies. In 1999, she was recruited to become Dean of Engineering at Duke. And at Duke, her vision and fundraising ability led to a tenfold increase in the endowment of the Pratt School of Engineering. Under her leadership, the number of women faculty in engineering grew from 6% to 19%. In 2007, she left Duke to become the provost and senior vice president for academic affairs at the Johns Hopkins University, where she led a university-wide strategic planning process and bolstered leadership in research, new programs, and graduate programs. In 2009, she was appointed Undersecretary of Energy in the Obama administration, where she was responsible for unifying and managing a $10.5 billion energy and environment portfolio. In 2011, she left the Department of Energy to co-found Cube Hydro Partners, LLC, that's focused on building and operating hydropower plants in North America. And finally, in 2017, she was appointed the 13th Chancellor of the State University of New York system, overseeing 64 college campuses and the largest public education institution in the US. She supervises 64 different campuses with 1.3 million students annually and 90,000 faculty and staff. She's a member of the National Academy of Engineering. She has 118 patents and is a member of the Inventors Hall of Fame. She received many awards, and she's a member of the board of directors of Cisco Systems. With that introduction, I'll introduce Kristina.
Good morning. Thank you very much for that introduction, Joe, and it's such an honor to be here. I mean, you made my morning when you mentioned that the quals are gone. I'm so excited. In fact, there's a professor here. Where's Dick Swanson? Dick, I'm gonna tell this story because we're a family, right? You promised to do my laundry during quals. This is a true story. Now, there's the rest of the story. I was actually going through cancer treatment at the time, and I know you were trying to be a good professor, but what department has faculty members that step up and do that? Our department. And that's why I'm thrilled to be here. I'm gonna follow, of course, an outstanding faculty member, a wonderful academic administrator, John Hennessy, and try and give a student's perspective of our department. So I came to Stanford in 1975. I found my way to EE because as a high school student, I've had a cold, so forgive my grovelly voice here, but I'll try and prevail here. I had done a science fair project, and I had used holographic imaging to plot the growth of a sporangiophore called phycomyces. It grew a few microns a minute. You can take a double exposure, you can look at the fringe patterns and see how fast it's growing. I had pretty good success, so the first thing I did when I arrived in that week of pre-orientation for class was to find the one faculty member on campus who did holography, and that was Joe Goodman. So I walked up the door, and I knocked on the door. Of course, what do you do when you're 18? You just expect they're just waiting around for you to come to the door. So I knocked on the door, and I showed Professor Goodman my hologram. as I was handing over the hologram. That was done in glass by the time. I know now, Bert, you're doing it all in digital, but I dropped it and it shattered. But I think he was so endeared to the enthusiasm that I started working that semester as an undergraduate, and I stayed all the way through my bachelor's, my master's, and my PhD. So I like to start out these talks by the why. You know, Simon Sinek's the why. So why did I stay? And one of the reasons why I stayed is because we had outstanding faculty, phenomenal faculty, to mention 9. Now, these are 9 of faculty members, left to right. You have Joe Goodman, Jim Gibbons, Gene Franklin, Tony Sigmund, Cal Quaid, Al Makovsky, Steve Harris, Ron Bracewell, and Bernie Woodrow. How could you not succeed with that kind of lineup? And in addition to folks I didn't have in the class, but were still important that I looked up to, people like Dick Swanson, independent. I did not take him up on doing my laundry, let you know. And Jim Harris and others that are here today. Jim Plummer, we used to run together, and just were so important to me in my career. So that's a really great reason to have stayed. And I always like to say there's a good reason and a real reason for doing things. This was my dad in the middle. This was taken in 1967. He was an electrical engineer. He was a hydropower engineer, which kind of circle back why I did cube hydro, but that's a different talk. And he taught me that what do engineers do? They do big projects. They build things. That's what we do. That's what this department has always done. We'll continue to do for the next 100 years. My dad passed when I was a sophomore. That's when you declare your major, and I decided that I needed to find out what he loved about electrical engineering. And that sustained me through those awful qualifying exams. So what I'd like to do today, just in the time that we have, is talk about 3 subjects taught by 3 faculty members that made an enormous impact on my career. So as an undergraduate, I studied lasers and nonlinear optics. I had Tony Sigmund, who taught me the beauty of the quarter wave plate. You have to be an engineer to understand this. I had taken EE 264, so I knew what impedance matching was. But what Tony did was bring it to life and to make it understand that these thin films stacked up, could be thought of as impedance matching and be anti-reflection codes. I even asked one of my old professors, Bert Hesselink, to bring one today, which I did, but I forgot to bring it up. I was going to show you. Anyway, these dichroic stacks. The other professor I had was Steve Harris, who is here, and nonlinear optics. Now, Steve, you taught a really interesting kind of nonlinear optics. You taught Jones matrices and Mueller matrices, and not necessarily second harmonic generation, 4-wave mixing, and all the cool things, or so I thought at the time, that were coming out. But you published a really important paper that we refer to as the Harris, Aman, and Chang paper. And what it showed is that you could stack birefringent elements and create an impulse response. And we know the relationship between an impulse response and an output optical network. It's a Fourier transform under certain conditions. We don't have time to go into those now. But it was really fascinating. And so when I got to the University of Colorado as a new assistant professor, my students and I reread this paper. We went into a little different direction because the kind of filters that you envisioned and you talked about in this paper were looking at astronomical prominences, stacking up a lot of these birefringent elements in the lower right-hand corner. And each one of those calcite crystals, birefringent is about 0.172, would give 2 impulses on the fast and slow axis. And depending on the orientation of the crystals and the number of crystals, you could actually resolve down to 1/8 of an angstrom. When we went in the other direction, we used the same mathematics and we actually designed a class of components called color polarizers. And they gave you very sharp transitions between bands, but instead of in the radio frequency, they were in the color frequency. And so these were 10 elements that we stacked up to give very crisp transitions between red, a primary color, and cyan, a complementary color. And I actually brought some here, which I may show in a minute. So this was really important, one of our first really important patents. And if we could do a passband filter, we could then do a stopband filter, and we could do a notch filter. So we created the best blue in the business, blue, green, and red filters. Now, once you have these in the paper, and if you go back and read Harris, Aman, and Chang, there's part 1 and part 2. I recommend both. it talked about how do you tune these filters. So it was envisioned at the time, it came out in 1964, either rotation mechanical or heating. Well, when I went to the University of Colorado, there was a chap in physics called Noel Clark, and I learned the power from Joe Goodman, Al Makovsky, and Bert Hesselink on cross-disciplinary research. So I went over to the physics department, and I learned about fast-switching liquid crystals. So we envisioned combining these color polarizers with fast-switching liquid crystals, and we created some very sharp, my student's name was Gary Sharp, very sharp filters, color link electronic color shutters. So we used our first stack, if you will, retarder stack, to separate white light into blue and yellow, as I show there. And these are what the filters look like. Now, one of the last times I gave this talk, we had overhead projectors. You'd be able to see them, but if you want to see them later on. But you can see that's a really nice blue. Our competition. Oh, don't drop it. Thank you. Well, I got smart. I started to make them out of plastic, which was awesome. Our competition was a dye-based filter. So the difference between using color polarizer filter and getting the nice transitions in a dye filter, we'll get to that story in a minute, why that made it was very important. So you separate first white light into blue along the x-axis and y along then yellow along the y-axis. Then you use a switch to either keep that orientation or flip it. Now, we did design filters, which if this is I don't know if you can see it, yeah, without this intermediate polarizer, but one of the first implementations had an intermediate polarizer, and that's selected between blue and yellow. Then we followed it with another color polarizer, the red cyan, and that would switch then between red and green. And your output would give you 4 different states and 4 different colors. Well, the advantage of this particular device was it switched at sub-microsecond times, which meant you could actually take a 3 CRT, now you have to remember this is back in the 90s, so our projection was done by cathode ray tubes, and you used one with a blue filter in front of it, literally a plastic, one with a green, one with a red. And as you can see, this is a very big, bulky projection system. And it was expensive, and the colors weren't that good, and the resolution of a CRT, if I remember, is something like 300 dots per inch. So it was not high resolution, it was big, it was bulky, it was expensive. I didn't realize it had one key feature that I would not have. So we started a company, and we built liquid crystal reflective displays on silicon, and we were able to replace those 3 RGB systems with a single little beam splitter and a color shutter, and create something that was quite compact. In fact, it is something that I can hold in my hand. Now, I thought this was awesome. I did not take a marketing class at Stanford, and to my great dismay, I should have. But for 1 week, I decided that I was so excited about this technology. It was so elegant. It was so wonderful that I was going to travel the world, which I did. I went to see a customer a week for 48 weeks because I was trying to sell them a color sequential liquid crystal on silicon display because one, it was cheap, compact, lightweight, high resolution, great contrast ratio. We had over 1,000 to 1 and about 2,500 dots per inch. I thought everybody's gonna love this. Well, I ended up going to Japan, and I spent 2 weeks in Japan. I visited every computer company and display company in Japan, 4 or 5 meetings a day for 2 weeks. And every time I'd show up, they said, yeah, we understand color sequential, we don't want that. We want 3 panels because we value brightness. Now, when you're doing color sequential, you're roughly 1/3 as bright as a 3-panel system. Well, after about 20 of these meetings, I'm thinking, okay, we got to reinvent. So I looked at this particular system, and it had a fatal flaw. So what this is, if you can see this here, you've got a lamp to the left, which is in black, comes into a beam splitter, gets reflected to these 3 funny-looking prisms, which is actually what this is. It's called a Phillips prism. And then they separate out red, green, and blue light, bounce off the 3 different panels, and if you're looking at a red, green, blue scene, like a blue sky, green leaves on a tree, and a red apple, Then the red apple will be displayed on one panel, the green leaves on another panel, and the blue sky on a third, and then they fuse together and get projected on the display. Here's the problem with this. And this is where what I call the Bert's laws were violated. So I took a machine shop course from Bert Hesselink, and he told me there's two things you have to know about making things. The first is never have one element do two functions. The second is make things square. They're cheaper. Well, here's the Phillips prism, and it violates both of those. One, it is not square. This thing cost $250 and was never made cheaper, even in volume, and it never got to volume. And the reason it never got to volume was the contrast ratio never really got above 5:1, unless you had about 5 PhDs tweaking it, which was not cost effective. And what happened is the white light coming from the left, which I've sort of shown as red, green, and blue, the first surface not only splits color, but it also reflects light. Now, this was originally designed for a 3-shot Sony camera system, where you'd have 3 different imagers. Well, what's the difference between a reflective display and an imager? Is in one case, you use unpolarized light and you absorb that. In the other case, you reflect that light out, and it was polarized because these were liquid crystalline silicon. Now, you know that polarization rotates ever so slightly when you reflect off of things, especially when you're splitting colors. So it violated both of those principles. But what we were able to design is the color quad. And the color quad used our color polarizer technology in front of a beam splitter. So white light would come in, and it would orient yellow on the S polarization, blue on the horizontal, which would get transmitted, yellow would get reflected. And then the next place, you would split you have another polarizer stack, which splits yellow into red and green. And then you recombine them. So we ended up building, I don't want to put a thumbprint on this, that would be very bad in front of all the optics faculty but if I can get this right. So this was the color quad. And we ended up making 10 million of these. We cornered the market for 7 years. We were in every rear projection display system that you could buy in Circuit City or Best Buy. When I was bored, I'd go into Circuit City or Best Buy, and I'd walk up and I'd say, "Can you tell me about this system?" And because I love to get mansplained about this, right? No, just kidding. And they'd try and explain, and I'd say, "Well, but why do you get contrast ratios of over 5,000 to 1? And it's because those color polarizers were so sharp and could differentiate the color so beautifully that we, as I said, kind of cornered the market. Well, I said it was for 7 years. And that's because not only was Moore's Law marching along after 7 years, but LCD, liquid crystal display, flat panel technology was going to eat the lunch of all the projection, front projection, rear projection. So we had to morph to movies, really big screens where it would take a long time to have liquid crystals eat our lunch. So what we did, and you may have seen these glasses, they're something that the Stanford nerds would be very proud of, I know. And if you've ever seen a Real D movie, there's about 300 or more of them. So we designed these because what you would do to make 3D in a stereoscopic sense is you'd look at one scene from one angle with one polarization and the other scene from another angle with an orthogonal polarization. Now, the monster of the Black Lagoon from the 50s never made it because the reason why is they only had dipolarizers. So you were separating one scene through, say, this particular dipolarizer, and the other scene through his complement. If you look at the spectrum of this, there's overlap, and you got ghosting. Didn't look very good. But with something that could get up to 10,000 to 1, these glasses, which are just retarder stacks, coming back to Harris, Oman, and Chang, were able to really distinguish those two scenes, and so your eye would see two different images from two different angles and fuse it into a 3D picture. Now, the interesting thing is if you ever go to an IMAX or you go to a Real D, you put these glasses on and you move your head like that, you'll still see no ghosting. And that's because if they were using linear polarization, as you move your head, you get a projection of the one scene on the other scene and creates ghosting. So coming back to Tony Sigmund, I remember that beautiful quarter wave plate we talked about earlier. And we created what I would call an oxymoron, an achromatic quarter wave plate. So we take these linear orthogonal states and create circular orthogonal states. And that's why as you turn your head, you still see perfect extinction or near perfect extinction for those two scenes. Our big breakout movie was Chicken Little in 2005. What can I say? And then Avatar. Avatar was the first movie to gross $2 billion. It won 3 Academy Awards, including one for Best Visual Effects. So not only are the glasses, but the projection optics and some of the other elements that gave it that brilliant blue. So I just want to conclude with a few things, and that is, I also had the great fortune of taking these 3 classes simultaneously. I took Fourier optics from Joe Goodman. I took Fourier transforms from Ron Bracewell, and I took adaptive signal processing from Bernie Woodrow. And what was interesting is going from class to class, you started to connect the dots. We were making as a master's project a vector matrix multiplier, which of course people use to do deep learning if you add in multiple layers. We had LED arrays at that time. We didn't have VXLs. This is a later rendition. And by imaging in one dimension and taking the Fourier transform in another dimension, which is the combination of a cylindrical and spherical lens, you can actually take one of the points and multiply by the matrix and then use the orthogonal lenses to sum them up. Well, what I realized is that there were errors and aberrations that I could correct by manually changing the little elements in film. This is 1978. We didn't have spatial light modulators then. We didn't have liquid crystal TVs. But when I went to the University of Colorado, I realized that we could go back and build a lot of the systems that we had designed and developed and do dynamic, real-time, what's called deep learning. We called it neural networks then, using these cascaded LCOS displays. This is one of my PhD students, Ram Naraswamy, who built basically a 2-stage, and I won't go into much detail here, but an optical box that would able you to do very high-speed optical correlations of very large imagery, which at the time was a problem that looked uniquely solvable by optics. We did sell it to Cytic, who went public, and sold to Hologic. And then we took another box that could find speculated masses in mammograms, developed that, sold it to Meditech, which was then sold to Kodak. And this is just a picture of an original slide with cells on it that some are cancer, some are not. And the key, actually, it turns out, is not finding every cancer cell. Find half of them, there's enough, but not finding the false positives, which we're able to do. So I think that what I'd like to conclude with, I have, I did go to the Department of Energy. I'm a firm believer that we need to do something about climate change imminently. It's been 10 years since I served there. I got out. I went and formed a hydropower company. This was the first. There's 80,000 dams in the US and only 3,000 produce electricity. A lot of those dams are not going to go away. Some should, without a doubt. But the ones that are there could be powered, and it could help with the future. We did build the company up, 19 plants on 10 rivers in 5 states. And about 3 weeks ago, we sold it. And that's why I decided it was time to go back to my true love, which would be academia, because of my incredible experience of 8 years in this beautiful department. So I'd just like to conclude with just musing about the next 125 years. And these are very broad brush things, but we've always been a place where we've done cross-disciplinary research. That's what I did when I graduated in 83, 84, working in Joe Goodman's group in Information Systems Lab. We've got big problems. I think the data analytics and machine learning overlaid on every discipline is a no-brainer. I know you all know that. Can we apply it to mitigating climate change, protecting the environment, addressing some of the NAE grand challenges, and broadening our impact? I think the second thing is, I think a grand challenge or an opportunity is how we diversify our faculty and students and staff. I love to see the increase in women. When I was at Stanford, I had, as you know, wonderful faculty, many that are here that I love dearly. I didn't have any women in any technical subjects. I did have 2 women faculty, one in psychology, worst grade I ever got. Psychology of sex roles, that's another talk. And the other one is communications. But I think it's really important that our faculty, students, and staff reflect the diversity of our society. can we attain gender parity and fully reflect that diversity? And then last, which I think is, when you're number one, everybody's out to get you. I know we take great comfort in knowing everybody's out to get us, but maintaining our excellence and our influence as well as our affordability is just so crucial. So again, I'm honored to be here. I love you all. Thank you.